students, in this video I explain stability. So stability is one of the major parameter while we are designing a control system. So while we are designing the control system, we have to keep stability in mind. If the system is designed is more stable, then it is a good control system. So that stability is the major important parameter while we are designing the control system. So in this third unit, so we can explain what is stable or what is stability and how many methods will be there to find out a stability of a given control system that are explained in unit 3. So initially, what is stability? The term stability refers to the stable working condition of a control system is called as stability. Stable working condition. If you are designing one control system, it will give a stable output. So it will give 100% output in t is equal to 0 seconds, and it will give same output at t is equal to infinity seconds or t is equal to 100 seconds like that. So then the system is called as stable system. So any system or any control system where designed, the systems may be stable. Otherwise, the systems are not in good condition. So every working system is designed to be a stable. So what is the stability? So definition is a system is stable if its output is bounded for any bounded. So the bounded output for bounded input systems are called as stable systems. In that stability, different cases will be there. First one is asymptotically stable. Asymptotically stable system. A system which is asymptotically stable if in the absence of the output or input, the output tends towards to 0 or equilibrium state. So then the condition is called as asymptotically stable system. So a system is asymptotically stable if in the absence of the input, the output tends towards to 0 is called as asymptotically stable system. Second one is limitedly stable or critically stable or marginally stable system. For a bounded input signal, if the output has constant amplitude oscillations, then the system may be stable or unstable. Under some limited conditions, such a system is called limitedly stable or critically stable or marginally stable system. So these systems are stable for limited or critical or marginally stable conditions. Those systems are called as limitedly stable systems or critically stable systems or marginally stable systems. Next one is absolutely stable system. If a system output is stable for all variations of its parameters, then the system is called as absolutely stable system. Next one is conditionally stable system. If the system output is stable for limited range of variations of its parameters, then the system is called as conditionally stable system. So these are the different types of stability. So are stable systems. So asymptotically stable, limitedly stable, absolutely stable, and conditionally stable systems. And the location of the roots on S plane. So based on this condition, so we can easily say the system either stable or unstable. So location of the roots on S plane for the stability. Consider m of s is equal to the differential equation numerator part and denominator part. So the numerator part and denominator part can be written as poles and zeros. In generally, poles are there in denominator, zeros are there in numerator. So that numerator can be converted as s plus z1, s plus z2, s plus z3 and so on. Denominator can be converted as s plus p1 plus s plus p2 plus s plus p3 and so on. So here z1, z2, z3 are called as zeros. P1, P2, P3 are called as poles. So this can be further modified or applying the so partial fractions, then m of s is equal to a1 by s plus p1 plus a2 by s plus p2 plus a3 by s plus p3 plus and so on an by s plus pn. Like that we can write this transfer function. Therefore, the transfer function location of the roots on S plane. So impulse response or inverse Laplace transform of the sketch of the time domain functions. So based on these two parameters, these two conditions, we can say the system is either stable or unstable. So for example, m of s is equal to a by s plus a. This is one system. So therefore, in S domain, a by s plus a. Now I want to convert this transfer function into time domain m of t. Therefore, m of t is equal to inverse Laplace transform of a by s plus a. That is equal to a into e power minus at. So this is in S domain. This is in time domain. So now I want to draw S domain graph and time domain graph. So this is the S domain graph. S is equal to minus a. So that is one pole in S domain, and I want to draw the output waveform for m of t is equal to a into e power minus at. A into e power minus at is nothing but exponentially decreasing. So this is the graph for a into e power minus at. So therefore, the roots on imaginary axis in S plane and response is exponentially decaying. So this is the first case, S domain, and this is time domain. So next case, for example, the transfer function m of s is equal to a by s minus a. Then the poles are located like this in S plane, and I want to write the time domain equation for this transfer function. M of t is equal to L inverse of a by s minus a, that is equal to e power minus a at. So the output graph is like this. So next one, for example, transfer function m of s is equal to a by s plus a plus jb plus a by s plus a minus jb. So this is complex conjugate poles. Real part and imaginary parts will be there. So that these are located in the S plane like this. And I want to write the time domain equation for this m of s. Therefore, m of t is equal to, so L inverse of a by s plus a plus jb plus a by s plus a minus jb. So after applying the inverse Laplace transform, finally it can be written like this, and the graphical representation of this equation is like this. So this is the next case. And next case, m of s is equal to a by s minus a plus jb plus a by s minus a minus jb. And locate these poles on S plane like this. And I want to write time domain equation. M of t is equal to L inverse of a by s minus a plus jb plus a by s minus a minus jb. And applying the inverse Laplace transform, and finally we can draw the waveform. The waveform is like this. So this is the next example. And next example, m of s is equal to a by s plus jb plus a by s minus jb. So these poles are located on S plane like this. Now I want to draw the equation for the time domain. M of t is equal to L inverse of a by s plus jb plus a by s minus jb. And applying the inverse Laplace transform and draw the output waveform. Output waveform is like this. So finally, so next example is a by s plus jb whole square plus a by s minus jb whole square. And the roots are located like this, and the output waveform in time domain is like this. So next one is a by s. So a by s is located on S plane is like this, and the time domain specification for a by s is equal to a. So a is the constant, so output waveform is like this. Next one is a by s square. So a by s square is located on S plane is like this, and the time domain output waveform is like this. So response is linearly increasing with respect to time. So these are the different S domain locations, poles locations, and the time domain output graphs. So by comparing all these parameters, we can finally conclude that, so when the system is stable, when the system is unstable. Already we know for the bounded input, the output bounded output, then the system is stable, and for the bounded input, for the bounded output, so that the system is stable, otherwise the system is unstable. So first we have to see where the poles are located, so where then output waveform is either bounded or unbounded. So after that we can say finally conclusion, so when the systems are stable and when the systems are unstable. So these are uh, different graphical representations in S domain and time domain.